Pressure due to fluid column at rest. Introduction. Have you ever wondered why your air pops when you dive underwater or when you are climbing a hill? Today, we are diving into a concept of pressure due to a fluid at rest, also called hydrostatic pressure. Let's get started. Real life example: climbing a mountain. Pressure decreases as we go up. A mountaineer climbing up a mountain experiences less pressure as they go up. Diving into a pool. Pressure increases as we go down, but someone diving into a swimming pool feels more pressure as they go deeper. Why does this happen? Because of fluid pressure, also known as hydrostatic pressure. The pressure in a fluid at rest. Pressure increases with depth. Here you have a container which contains water whose density is rho. Imagine we have a column of water inside a glass cylinder. It has two layers, one is the top layer and the bottom layer. The pressure at the top layer is P1 and the pressure at the bottom layer is P2. The area of cross section of the layer is A. The top layer is at a depth H1 and the bottom layer is at a depth H2. At the top of the water, the pressure is P1 and at the bottom, the pressure is P2. As we go deeper, pressure increases because the water above is pushing down due to its weight. The top of the water column is at a depth H1, the bottom is at a depth H2. The area of the cylindrical cross section is A. Here you have a force F1 equals P1 times A, which is acting downward. This force is nothing but weight of the water above the top layer of the cylinder that acts in the downward direction. Next, there is another force at the bottom of the container, F2 equals P2A. This F2 force is nothing but the force that holds the weight of the water in the cylinder plus the force F1. Fg equals m times g. Fg is the weight of the water in the cylinder that acts downward. Force at the top, F1 equals P1 times A. Force at the bottom, F2 equals P2 times A. F1 is in the downward direction, F2 is in the upward direction. The water in between has a mass m and density rho. It experiences a downward gravitational force, Fg equals mg. Let's write all three forces here. F1 equals P1 times A, that's in the downward direction. F2 equals P2 times A, that's in the upward direction. And the Fg is in the downward direction, that's the weight of the water in the cylinder. The mass is replaced by volume multiplied density. Volume is replaced by H2 minus H1 multiply area. Let us go for a balancing force equation. We get F2 equals F1 plus Fg. So, the F2 is replaced by P2 times A, F1 is replaced by P1 times A, plus Fg is replaced by H2 minus H1 multiply A rho G. This is an important equation, let us write it here. Final formula, very important. If we take surface of the liquid as the top level, P1 equal to PA, atmospheric pressure. the top layer is being raised to the free surface of the liquid. Thereby, the pressure P1 becomes atmospheric pressure Pa and H1 becomes 0, and the depth of bottom layer becomes H. Depth H as the bottom layer P2 equals P. Then the formula becomes P equals Pa plus H rho G. Pa is the atmospheric pressure and P is the pressure at a depth H from the free surface. H is the depth. And if we ignore the atmospheric pressure, then P equals H rho G. The pressure depends only on the depth but not on the area. Let us spin these two formulae. The key point: pressure only depends on height, not on the shape or width of the container. Pressure due to a fluid column at rest P equals H rho G. Here we are not considering the atmospheric pressure. Hydrostatic paradox. Imagine 5 containers of different shapes, all connected at the bottom and filled with water. Even though they look different, the water level is the same in all because the liquid seeks its own level. Because at the same depth, pressure is the same, no matter the container shape, because pressure depends on H rho G, but not on the area. But remember, the weight of the liquid at each column will be different. Atmospheric pressure. The surface air pressure or atmospheric pressure equals weight of air in column above unit area. Now, as we go up, the atmospheric pressure decreases because as we go up, the air above our head decreases, so pressure decreases. Atmospheric pressure is caused by the weight of the air above us. It decreases with height. 1 atmospheric pressure equals 1.013 multiplied 10 power 5 Pascal. This is at sea level. Cooking takes longer at high altitude because of low atmospheric pressure. People may get nosebleeds due to pressure difference between body and air. Some activities. Collapsing container. Here there is a container. We heat it so that the air molecule inside or the water molecule inside gets evaporated, and we close the mouth and pour cold water into the container. We found that this container collapsed. Take a metal container, remove air from inside using a vacuum pump. What happens? The container collapses. It's because air pressure outside is greater than inside. That crushes the container. Another activity, upside down glass trick. We pour water in the glass tumbler and cover with the cardboard. We immediately flip it up and down. Then we find the cardboard does not fall. Fill a glass tumbler with water. Cover it with a cardboard. Flip it upside down carefully. It's a big surprise. The water does not fall. Why? Atmospheric pressure pushes up on the cardboard holding the water inside. Summary. Let's quickly recap. Pressure increases with depth. P equals H rho G. It does not depend on shape or area, just the height. Atmospheric pressure is always around us. It plays a big role in daily life, cooking, and even fun experiments.